Hi guys! You should now have the mathematical knowledge to properly use and understand control theory. This is why this will be our first lecture about it. We will now look into open loop control. First of all, what are the objectives of control? Well, we want the system's output to match a desired reference. You're familiar with the diagram here. We have an input signal ut, whose Laplace transform is us. We have a block representing the transfer function gp of the dynamic system or the plant. And we have its output yt, whose Laplace transform is ys. Given a dynamic system, gp in this case, the aims are to ensure that the system's output response yt follows a specified reference rt depending on the system's input ut. And we have to do this despite external perturbations. The reference has to be the output, whatever the perturbations that are pushing it away from what it should be. It should always correct itself to stay on the reference. This is the goal, the objective of control. To make this a little bit clearer, imagine that you're walking on a pavement trying to follow a white line on the floor. Suddenly, a big gust of wind comes in and pushes you away from that line. Well, your brain and your leg muscle and your core muscles are going to push and work together to balance your body and stay exactly on that line where you want to be despite the new perturbation of the gust of wind. So this is control. Okay, it's trying to stay on the same output despite all the perturbations and everything else that's going on. So here we have our dynamic system or plant represented by the transfer function gp, its input ut, and its output yt. So gp is described or modeled by certain system dynamics expressed through differential equations, also called the transfer function. So we have seen all this. Well, in the real world, the input ut is often provided by actuators. So for example, if you're driving a motorcycle, you're going to use the throttle as an actuator, which becomes the input to the system that is the motorcycle. Same thing if you're driving a car, you're going to use the pedals to give the input, and the input is provided by the actuators because the pedal is an actuator. The output is often provided by sensors. So to make this clear, of course the output, which is the speed, the velocity, is actually provided by the car or the motorcycle. But what I mean here by provided is that it is provided to us. So we need to have a way to measure the output to be able to know how our control is going. So in this case of the motorcycle or the car, the output is actually provided by a speedometer, which is a sensor. Let's now look at the example of adaptive car cruise control. So here we have a car equipped with a radar transceiver. This radar emits electromagnetic waves which bounce around the environment of the car to tell it how far are its closest obstacles. It's also equipped with a speed sensor, such as a speedometer, to tell the car exactly how fast it is going. And finally, it has a throttle to actuate its speed. So it has something to play with its speed and actually change it, which is the actuator. And then it has something to tell it how fast it's actually going, and then something else to tell it, okay, wait, there's an obstacle in front of you, you actually need to slow down. So in the end, the tasks of adaptive cruise control are first to retain a constant speed if there is no car in front, and second, to retain a constant distance to the car that is in front of it, if there is a car in front. Let's look at another example that is really relevant to this course and more approachable: the speed control of electrical motor. So ensuring that an electrical motor is turning at the velocity we want it to be turning. So first we have the motor dynamics GP, which are modeled by the equation you can see here. So it looks very complicated, but it is a normal differential equation for an electromechanical engineering system, something that we saw in one of our first lectures. So here the output signal is the measured velocity of the motor. So theta dash, which is the first derivative of theta, which is the angle of rotation of the motor. The input signal is the voltage. So by changing the voltage, you essentially can change how fast the motor is rotating. What changes the input voltage is the actuator. What measures the output signal or the velocity is the sensor. So we also have a demand signal, which is the desired velocity of the motor. How fast do we want the motor to actually rotate? The first graph presented in this slide is actually a plot of the measured velocity of the motor in two cases. One is good control, which is the green curve. The other one, the red curve, is actually bad control. You can also observe a straight line very close to the good control curve, which is actually our demand signal, the desired velocity for the motor to rotate at. The second graph is actually a plot of the voltage input in the case of good control and in the case of bad control. So first of all, looking at the velocity, you can see that good control stays very close to the demand signal. At some point, there is kind of an instability that comes in. The signal struggles a bit. And this, you can see, is at the point of time where load takes effect. That means that at this point, something is connected to the motor. So the motor has to actually rotate an extra load, which changes a bit its dynamics. In this case, the actual velocity goes down, but that control acts and it goes back up very close to the demand signal. You can see that little spike. Well, in the case of bad control here, first of all, the red curve before the point of time where load takes effect is not exactly where it should be on the demand signal, and it gets even further once the disturbance of the load comes in. If you look at the voltage curve, so the input curve, you can see that the bad control signal is actually very constant at a value that would seem to be right, but is actually not right because the dynamics of the motor change everything. Okay, so bad control is not reactive, and bad control leads to a velocity that is actually not the one you want. Okay, because it is not that straightforward to obtain the things you want in engineering systems. The good control curve, on the other hand, is quite counterintuitive because it is much lower than the bad control curve, which is providing a velocity that you don't want, that is actually lower than the good control curve in the case of velocity. And it then goes up after the point of time where load takes effect to compensate for that new load and help the motor keeps its velocity. So this is quite a complete example of what control is, how we can have good control, bad control, and what we are effectively aiming for. So how do we design a controller? Well, there is a generic procedure for that. First of all, you have to determine the system dynamics of the plant GP. For this, you use mathematical models and Laplace transform to build the transfer function of the system. You then want to establish the control objective in a numerical manner. For example, say, okay, here we want to keep the car going at 25 kilometers per hour for, let's say, 2 hours. This is a numerical control objective. It's something that you can reach mathematically, clearly. 3, you have to determine a mechanism to generate the system's output you desire according to 1 and 2. So you have to find a way, actually the best way, to control your system in a way that will satisfy the objectives you want and will fit the transfer function of the system. So there are two options to do that. First of all, the open loop controller, and secondly, the closed loop controller. In this lecture, we're going to look at the open loop controller. So if you have YT, which is your output, which has to follow a reference RT, in this case, your demand signal. An easy approach is to choose that your input signal to the plant, ut, is equal to the inverse, so 1 over your plant, 1 over GPS, multiplied by the reference signal. Okay, so putting this in a block diagram form. First of all, we look at your plant. We have GPS, your plant, with an input signal ut and an output signal yt. But here, the input signal ut is actually the output of a controller, which is the inverse of your plant, so 1 over GPS, multiplied by your input reference. And we'll see why this works. So first of all, we take the Laplace transform. So the Laplace transform of RT becomes RS, and the Laplace transform of UT becomes US. Finally, the Laplace transform of YT becomes YS. Then you can write from this block diagram that YS equals GPS times US. And this is actually equivalent, again working with the block diagram you have above, to YS is equal to 1 over GPS times RS times GPS. Okay? Why? Because US is equals to RS times 1 over GPS. So you develop all that, and what you get is that YS equals RS. So essentially, YT equals RT. And why does this work? Because you want your reference to be your output. So all you have to do with your controller is to completely cancel your plants. Your controller has to counteract the effects of your plant, and therefore it has to be the inverse function. If you have transfer functions for each, it's very easy to do. So open loop control is actually extremely simple. All you do is, because you want your output to be equal to your reference, you build a controller that cancels your plants. It counteracts it so that your output is exactly your controller. So its advantages are obviously that it is fast and simple to implement. However, it has many disadvantages. First of all, you need to have the exact knowledge of the plant. You need to know exactly what is the transfer function of the plant to be able to create the inverse of that transfer function, in your controller. It will not react well to significant disturbances. Any disturbance that is significant will push the output of the system away from your reference input because it is not able to adapt itself to a new variable. Finally, the poles of the controller have to remain in the left half of the complex plane. The plant and the controller have to be stable. So to make sure that you get something that makes sense out of this, so a stable output, you actually need your controller to be stable on its own itself, but you also need your plant to be stable. So you have a lot of constraints to make this work, and even if it works, it won't be reactive, it won't be extremely useful in demanding conditions. This concludes our first lecture on control theory, more specifically open loop control design. If you have any questions, please do not hesitate to message me and ask me. I'll be very happy to help you. Thank you very much, guys.